Okay, I'm going to do my own version of Sal-Khan's optimizing box volume analytically. Really the only difference between my version and Khan's version is that I use the increasing-decreasing method for determining whether or not a critical point is a minimum or maximum, whereas he uses something that I haven't taught you yet, which is called the second derivative test. Really, you can solve any optimization problem using either method. Using the graphical method that Khan showed, he had already set up the problem as a sheet with an x by x corner cut out of each, an x by x box cut out of each shape, each corner, in order to form an open-top cube, and that open-top cube would have a volume which follows this function. He had also derived a realistic domain for that function as between x being between 0 and 10. And he had also tested the endpoints, in other words v of 0, and found that to be 0, and v of 10 is also 0. And this follows the extreme value theorem in that your extreme values are going to be either at your local minima, local maxima, or they're going to be at your endpoints. So we've ruled out the endpoints. Next thing we need to do is find critical points, use critical points to find local minima and maxima. Alright, let's go ahead and put this into a form, this equation into a form that is a little more amenable to our derivative identities as we know them so far. If you know a derivative rule called the multiplication rule, you could apply it at this stage, but in my case, in this case, it's relatively easy to FOIL this out, so we can FOIL it out and then use the power rule. I'm going to FOIL the two binomial terms out first. So this is going to be 600, minus 100 x plus 4x squared, and then multiplying through by x, that gives us a v of x equal to 600 x minus 100 x squared plus 4x cubed. And taking the derivative of this, that gives us dv dx is equal to 600 minus 200 x to the first power plus 12x squared. Following the general process for finding critical points, we set the derivative equal to 0. 600 minus 200 x plus 12x squared. Something I often do at this point when you've got a 0 on one side of an equation. Sometimes it makes life a lot easier. In this case, it doesn't make a whole lot of difference, but something I often do is divide through by common denominators, and also this is a quadratic equation, so I'm going to rearrange it so that the x squared term comes first. So that's going to be equal to 6x squared minus 100x plus 300. Alright, like I said, this is a quadratic, so we can apply the quadratic equation. So it's going to tell us that x is going to equal negative b, so that's positive 100, plus or minus the square root of b squared, so that's 100 squared, minus 4 times a, which is 6, times c, which is 300. All of this divided by 2a. Okay, working out the discriminant for this, that's going to be x equals, or actually let's copy down everything except the discriminant first. And our calculator says that the discriminant is 2,800, oh wait, forgot to take the square root, 52.92. And I rounded that off. It's not exactly 52.92. All right. Now, this gives us two possible answers, one of which is going to be wait a minute. No, sorry. They're both positive, but one of them's out of the domain. So if you take a look at your two possible answers, the positive answer, if the plus or minus is a positive, you get 152, or x equals 152.92. over 12. That's going to be higher than our maximum value of 10. So this is not a valid solution. If we use the plus or minus being a minus, then we get x equals 3.92. And since this is a word problem, don't forget to include units. Our initial measurements were in inches, so our final measurement should be in inches. Now, in this case, it is obvious that this is a maximum. So we can just call x equals 3.92 the value of x that gives us our maximum, and then go forward to find the volume corresponding to this. We know that this is a maximum for a couple reasons. Within our domain, we have only one critical point. On either end of that critical point, we have values that are clearly at the low end of our spectrum, of the spectrum of possible values. In fact, you cannot have a volume lower than 0. You can't really even have a volume of 0. So we know that just based on these two extreme values, these two endpoint values, we know that on either side of x equals 3.92 inches, the function is decreasing because it has to decrease in order to go from 3.92 down to 0. So that means that this is a maximum, it's our only maximum, and it's no higher than, and it's definitely going to be higher than our endpoints. So in this case, we know that this is a maximum. In other cases, we would have to do a little bit more work to determine that this is in fact a maximum value. And I'll show you how to do that in just a second. I say in just a second because you're not actually done yet. The problem not only asked you to determine the value of x that maximizes the volume, it also asked you for the maximum volume. So let's go back to this equation, or if you want, you could go back to this equation and plug the 3.92 into that. So v of x, I'll do this in, might as well do it in red. All right, so v of x is going to be 3.92 times 20 minus 2 times 3.92 times 30 minus 2 times 3.92. And our v of x, our maximized v of x, comes out to 1056.3. And since our units were in inches, our length units were in inches, that means our volume units are going to be in cubic inches. Okay, so that is the other half of your answer. And like I said, you can tell that this critical point is a maximum just by looking at the other numbers and how many critical points you have. That process, that logical process, usually does not work. So what you have to do instead is you have to determine whether the function is increasing or decreasing on either side of your critical point. So let's go through that. So I'm setting up here our test values. Test values for x on either side of the critical point. Up here, I've got a copy of our formula for dv dx, which I'll be using twice. Once on a test value below 3.92, which I arbitrarily chose as 3. 1 might not have been a bad answer either, because 1 tends to make things a little make the multiplication a lot easier. Sorry, I forgot the squared part on the formula up there. All right, we know that when x equals 3.92, dv dx is 0. Let's figure out what happens when x equals 3. All right, so that means that dv dx is going to be 600 minus 200 times 3 plus 12 times 3 squared. And what do you know? 200 times 3 is 600, so that and that will cancel each other out. We'll just be left with 12 times 9. Even if you're not real good at math, at arithmetic, you should at least be able to determine that this is positive. So over on this side, on the before the critical point, we have a positive derivative. That means it is an increasing function. And remember that a maximum is defined as you get a relative or local maximum when you goes from positive to negative, or increasing to decreasing. So let's check out the x equals 5 value. All right, plugging that into here, we get dv. Let's give myself a little more space here. Dv dx is going to equal 600 minus 200 times 5 plus 12 times 5 squared. Okay, so this is going to be 600 minus 200 times 5. That gives you negative 400 plus 12 times 5 squared is 300. And so that's going to be a negative number. All right, cool. So we got negative before the critical point, negative before the critical point. We got positive after the critical point. That means this is a maximum, which we already knew, but for other problems, it's not going to be not necessarily going to be quite as obvious. Okay, in general, these optimization problems can be rather complicated, especially since they involve word problems and a lot of complicated setup and possible substitutions. I have one more optimization problem in this playlist. I also have, Khan Academy also has maybe three other optimization problems. They all use the second derivative test, but you should at least be able to understand the Khan Academy videos on optimization, even if they except for that second derivative test part, which you don't need for my class. All right, so like I said, basically what I'm saying is if you want some more practice, if what the videos I'm providing with you are not enough practice, head over to Khan Academy and look at the optimization of sum of squares and a few other videos as well. But first, watch the next video.